Okay, so let us start today's session. In the last session, we have seen this simple cooling system. Okay, simple air cooling system. If I just okay, so this is a system that is simple air cooling system which we have seen in the last lecture. We have also seen the PV and TS diagram. Okay, now our purpose is to analyze this system. Okay, we were supposed to perform the analysis. Okay, of this particular system. Okay, so I'll just write down now. Okay, we are supposed to perform what? Analysis of the okay, analysis of the simple analysis of the simple air cooling system. Okay, as I told you in the last session, now we will analyze it. Okay, analysis of simple air cooling system. Okay, so that we will do now. Okay, so that this is the thing which will do it now. Okay, now see, let us see. Okay, all of you just focus on the diagram which is given. Okay, so as you can see, okay, the ambient air, you can see this is the ambient air. Okay, I'll just okay, increase this size. Okay, okay, so as you can see, all of you, now the ambient air, all of you know that ambient air, okay, it will be okay, it's the inlet condition. Okay, so this I will mark as point number 1. Ambient air will be at the inlet condition, so it will be, I will be marking this as point number 1. Okay, now this ambient air will be rammed. Okay, so I will get, after ramming, I will get point number 2. Okay, so once it is rammed, I will get point number 2. Okay, you can see the passage of the air. Okay, it is like this. Okay, so the air is flowing like this. Okay, so 1 is the ambient condition, that is the inlet condition, after which it will be rammed. Okay, once it is get ramped, we will supply it to the compressor. Okay, so after the compression, okay, at this particular point, see, all of you can see this, at this particular point, okay, will get, okay, the exit air. Okay, so that we will compressed air, that point we will call it as 3. Okay, I'm just highlighting it. Okay, so you can just zoom on your screen. Okay, so this is a point number 3 which I will get in. So 1 is the inlet, after ramming I will get point number 2, after compressing I will get point number 3. Okay, so the point number 3 is the outlet of the compressor. Okay, so this is nothing but inlet to the heat exchanger. So this is the heat exchanger. Okay, so 3 is the inlet to the heat exchanger. Okay, so at the exit I will get, okay, here at this point, okay, I will get, okay, all of you can see here. Okay, at this point I will get point number 4. Point number 4 is the exit of the heat exchanger. Okay, so point number 4 is the exit of the heat exchanger. Okay, now yeah, after the heat exchanger, it will go where? It will goes to the turbine. Okay, so it will goes to the turbine. So 4 is the inlet to the turbine. Okay, so 5 is the exit to the turbine. You can see this. 4 is the inlet to the turbine, 5 is the exit to the turbine. And from exit, okay, all of you, from exit, okay, it will goes to cabin. Okay, from 5 is the exit to the turbine, from where it will go to cabin. I'll just write down that word. Okay, after that it will go to cabin, and from cabin it will goes, okay, at 0.6. See, all of you, 4 is the inlet to the turbine. Okay, 5 is the exit to the turbine. Okay, exit to the turbine, we will supply it to the cabin, and once it is getting out of the cabin, okay, it is point number 6. Yeah, is that okay? Yes, same diagram. Okay, we have plotted on a TS diagram. Okay, same we have plotted on a TS diagram. Is that okay with this one? Yes.
Yes, sir.
Okay, now let us start analyzing the cycle. Okay, now we are supposed to do what? We are supposed to analyze the cycle. Okay, now see, obviously the aircraft will be moving at certain velocity. Okay, so I'll mention here v. Okay, v is nothing but, okay, it is nothing but aircraft velocity. V, it is nothing but aircraft. V is nothing but aircraft velocity. What is v? V is the aircraft velocity. Okay, v is the aircraft velocity, or this is nothing but, okay, air velocity relative to the aircraft. Okay, one and same. You can call v as the velocity of the aircraft or relative velocity of the air. Okay, which is passing through passing, okay, along the aircraft. Okay, so that I will call it as V. Okay, now see, whenever we have velocity, obviously there will be a kinetic energy. Okay, so I will write down now. Okay, kinetic V is the aircraft velocity. Okay, or you can also call this as velocity of the air. I will also write down, or it is nothing but velocity of the air, okay, relative to the aircraft. Velocity of the air relative to aircraft. Okay, it is having one and same meaning. Okay, it is nothing but aircraft velocity or velocity of the air relative to the aircraft. Now see, so what kinetic energy the air will be having. Okay, so I'll just write down now. Okay, so kinetic energy, okay, kinetic energy of outside air. Okay, kinetic energy of outside air, kinetic energy of outside air relative to the aircraft, relative to the aircraft. Okay, I need to calculate, okay, what kinetic energy the outside air is possessing. Okay, so how to calculate kinetic energy, all of you know. Okay, kinetic energy is given by, how to calculate that, it is given by half into mv square, right? What is the basic formula? It is half into mv square. Okay, now I'll just write down this as, okay, v square divided by 2000. Okay, v square divided by 2000 I will write down. Okay, v square divided by 2000. Is that okay? Yes, are you able to understand from where it is came? Yes. Yes, okay, I know that there will be a okay, you will not able to understand this. Okay, that is the reason why purposefully I written this formula. Okay, so I will just now go. Okay, now I'll just show you the, okay, now see how to write down kinetic energy. Okay, all of you know about this formula, half into m into v square. All of you know this formula, half into mv square. Yes.
Yes.
This is the formula for kinetic energy, half into mv square. Okay, so but mass is 1. Okay, if mass is equal to 1, okay, then what formula you will get? We'll get it equal to half, okay, v square. Is that okay? Half v square. Is it okay? But if mass is 1, we will get the formula, okay, half into v square. Okay, but see what we'll do. See, all of you see, if you want, I'll just write down this again. Okay, see here, all of you see, I'll just go through it. See here, all of you see, I'll rewrite this formula again. Okay, so it is half, okay, into m into v square, right? Half into m into v square, right? So I'll just write down now, half into mv square. Okay, but if mass is equal to 1, if mass is equal to 1, okay, our formula is given by half into v square, right? Our formula is half into v square. Okay, but this formula, see, this formula will give you the answer in kilojoule. This formula will give you the answer in kilojoule. Okay, while this formula, okay, that is half into v square, this formula will give you the answer in kilojoule per kg. It will give in kilojoule per kg. Okay, you can remember this, kilojoule per kg, because you assume mass as 1. Okay, see, half into m into v square, it will give the kinetic energy, right? Kinetic energy will be in kilojoule. Okay, but when you take mass is equal to 1, okay, you will get this formula, that is half into half into v square. Okay, you can see this, half into v square. So this formula will give you the answer in kilojoule per kg, because mass is 1. Okay, that means everything you are calculated for 1 kg, right? Everything you are calculated for 1 kg. Now see, all of you, okay, see this kilojoule. Okay, this you will get it in kilojoule only when mass, this velocity, it is in kilometer per second, right? See, this you will get it in kilojoule when velocity is in meter per second, kilometer per second. So when velocity is in kilometer per second, this answer will be in kilojoule. Okay, but what we used to do is we used to take velocity in meter per second. Okay, so see, all of you, I'll just erase this. Okay, I'll just erase kilojoule term. I'll just erase kilojoule term. Okay, the reason is that, okay, why I've erased this term? as you can see, why I erase this term? Because we have the habit to take velocity, okay, in meter per second. Okay, so this half into mv square, it will be in joule, okay, if velocity is in meter per second. Okay, so if velocity is in meter per second, we will get answer kinetic energy in joule, right? Similarly, if you take mass is equal to 1, our answer becomes joule per kg, right? Joule per kg, right? Now, okay, now see, if I want this term in kilojoule per second, sorry, kilojoule per kg, if I want this to be in kilojoule per kg, so what I will get? I will get it like this, okay, half into v square. Okay, you can see this half into v square. I will write down this as a v square. Okay, 1 into v square, I will write down as a v square. And this joule, if I need to convert into kilojoule, okay, I need to divide by 1000. Okay, I need to divide by 1000. Okay, so what I will do, v square by 2, okay, divide by 1000, divide by 1000. Yes. Okay, so what answer I will get? I will get an answer equal to v square by 2000. I will get answer equal to v square by 2000. Okay, and this is in kilojoule per kg, right? Is that okay? This is in kilojoule per kg. Yeah, let me know.
Yes, sir.
Okay, see, basic formula, what is that? Half into mv square. Okay, what habit we have? We have the habit to take velocity in meter per second. So when we take velocity in meter per second, okay, when we take velocity in meter per second, we will get answer in joule. Okay, so but if we assume mass is equal to 1, okay, so in that case, okay, half into mass is 1 into v square. Okay, so this answer we will get it in joule per kg, because in this equation, when you assume mass is equal to 1, every answer we will get for 1 kg of mass, that is per kg, right? Now see, this is in joule per kg. If I need to convert that into kilojoule per kg, I need to divide by 1000. That's why I'm getting v square by 2000. Yeah, is that okay? Yes.
Yes, sir.
Now let us start. Okay, let us start deriving the next part. Okay, so now what we need to do? Okay, so this is all about the kinetic energy. Okay, now this kinetic energy, okay, I will write down the energy balance equation now. Okay, try to understand. Now I will write down, okay, energy balance equation. Okay, so what is energy balance equation? All of you know what is energy balance equation. Okay, what is the energy balance equation? Yes, what is the energy balance equation? See, we are also seeing the steady flow energy equation. Okay, we have seen the steady flow energy equation. In that, okay, I'm just directly write down that as S2 minus H1 is given by S2 minus H1 is given by V square divided by 2000. Okay, so this is the energy balance equation. Energy at the inlet is equal to energy at the outlet, right? So this is what the energy balance equation is. So it is somewhat similar to steady flow energy equation, which we have seen in the thermodynamics. Okay, what was that? Okay, change in see, we used to write down q dot minus w dot is equal to delta ke plus delta pe plus delta h. Are you able to remember that equation? Yeah, let me know. See, this is the energy balance equation.
Yes, sir.
Okay, so this is the energy balance equation, okay, which I've written, that is energy at the inlet is equal to energy at the outlet, right? So okay, so this is the energy balance equation. Now you know that how to write down enthalpy. Enthalpy is nothing but, okay, Cp into T. Okay, so Cp into T, that is enthalpy. Similarly, what is H1? It is Cp into T1. Okay, that is H1. So is given by V square divided by 2000, right? Is given by V square divided by 2000. Is that okay? Yes. How to write down enthalpy? Enthalpy is simply Cp into T, Cp into T, right? So now what I will do, okay, see, all of you can see that, okay, Cp is the common term. Okay, Cp is the common term. So if I take it Cp common, okay, what is remaining? Okay, what is remaining here? It's a T2 minus T1.
T2 minus T1.
Right? T2 minus T1. Cp, if I take it common and if I bring it that into the right hand side, okay, it will go into the denominator, right? So it will go into the denominator. Yeah. Is that okay? Yes, we will fastly go through that expression. Yes, right. Now see, I'm interested to get the value of T2. Okay, why I require T2 is, okay, see, T1 will be given, right? T1 is the inlet condition. Obviously, it is to be mentioned in the problem. Okay, what I need to calculate? I need to calculate T2. Okay, now what is T2? As you can see in the diagram, what is T2? T2 is the temperature after ramming. Okay, so once you ram it, we need to get that temperature. Okay, so that temperature I want, that is T2 I want. So T2 minus T1. That's why how I written, I taken Cp common. So Cp will go on the right hand side. It will be in the denominator. Okay. So now I need to get the value of T2. Okay. So I'll just write down it as, now I just write down it as, so T2 is given by, okay, this T1 plus, okay, V square divided by 2000 into Cp. Okay. 2000 into Cp, right? Is that okay? Yes. Even I will
Yes, sir.
right hand side, it becomes in plus. Now see what I'm doing. Now what I will do, yes. Now see here, what I will do now. See, when you divide this entire equation by T2, okay, sorry, T1. Let us divide this entire equation by T1. Okay, so I'll just write down now here as, okay, you can see here, okay, dividing above equation by T1. I will divide this equation by T1. Let us see what I'm getting. Okay, so here, okay, as you can see, now what I will get, all of you. So now what I will get is, okay, I'll just write down now as T2 by T1. Okay, T2 by T1. Now T1 by T1 is 1 plus V square divided by 2000 Cp into T1, right? Because I will divide this above equation by, I will divide above equation by T1. Okay, so this is the equation which I will get. Now see all of you see here, T2, what is that T2? You can see T2 is the temperature after ramming. You can see T2 is the temperature after ramming. So whether you go ideally, that is 1 to 2, or whether you go actually, that is 1 to 2 dash. See, I already told you 1 to 2 is the ideal process, 1 to 2 dash it's the actual process. Okay, so but whether it's a ideal or whether it's a actual, okay, we need to get same temperature. Okay, so instead of T2, you can write down that as T2 dash. Okay, instead of T2, you can write down that as a T2 dash, right? So how to write down that? Yes, how to write down that? Yes, so instead of T2, what I will write down now, instead of T2, okay, I'll simply replace T2 by T2 dash. Okay, it is one and same. So see here how I'm writing, T2 I'll replace by T2 dash. So T2 dash by T1 is given by 1 plus V square divided by 2000 Cp into T1. 2000 Cp into T1. Simply, I'm just replacing, okay, T2 by T2 dash, right? So whether it is T2 by T1 or whether it is T2 dash by T1, okay, it is one and same, right? Now see, all of you, in the thermodynamics, okay, we have seen the relation, okay, relation between Cp and Cv, okay, all of you. Are you able to recollect this relation? Okay, we have seen that Cp minus Cv is equal to R, right? Cp minus Cv is equal to R. Okay, so if Cp minus Cv is equal to R, right? If Cp minus Cv is equal to R, right? So what I will do, okay, I will take Cp common. Okay, so when I take Cp common, what is remaining? 1 minus, okay, 1 minus Cv by Cp, 1 minus Cv by Cp is equal to R, right? Is equal to R. Is that okay? Yes, try to understand. Is equal to R, right? So now see Cp minus Cv is equal to R. All of you know this. This we already seen in the this thermodynamics, right? Cp minus Cv is equal to R. We already seen that in the thermodynamics, right? Now what we'll do, okay, Cp when I take common, okay, it becomes 1 minus Cv by Cp minus, okay, 1 minus Cv by Cp is equal to R, right? So now let us focus on this equation. Okay, now let us focus on this equation. Okay, now what we'll do here, okay, all of you. So what value of Cp I can put now? Okay, see all of you. So Cp, I'll just write down as it is, Cp 1 minus. Now see, all of you know that Cp by Cv is gamma, right? What is Cp by Cv is gamma. So what is Cv by Cp? It's 1 by gamma. So it's 1 by gamma is equal to R, because Cp by Cv is equal to gamma. Cp by Cv is equal to gamma. So when Cp by Cv is equal to gamma, okay, what is Cv by Cp? It is 1 by gamma. Okay, that is what is written, right? So from this, okay, I will get the value for Cp as, okay, so I need to get the value for Cp. Okay, so Cp I can written as gamma minus 1 by gamma, okay, is equal to R. Gamma minus 1 by gamma is equal to R. Okay, so from this I will write down the value for Cp as, because I need to get this value for Cp. So what value of Cp I'll write down? Okay, Cp I'll just write down as gamma into R upon gamma minus 1. Okay, gamma into R upon gamma minus 1. So this is a one equation. Okay, what I got, okay, I will call this as one more equation. Okay, so let me call, okay, this as, okay, so above equation. Okay, so see, let us call these two equations above equations. Okay, let us call them as equation number 1. Okay, and now let us call this as equation number 2. Okay, this is the equation number 2. We will go, right, we got, right. Now what we'll do, okay, we will put the value. Okay, so putting value of Cp from equation number 2 into equation number 1. Okay, so let us put that value. Okay, so we'll put that in any one of the equation, we can put that. Okay, so I'll just write down that. Okay, so what is equation number 1? T2 by T1 is, okay, let us write down that. Okay, so T2 by T1, okay, it is same as what? T2 dash by T1, okay, is equal to what equation we have? We have the equation 1 plus V square divided by 2000, 1 plus, okay, V square divided by 2000, okay, V square divided by 2000, you can check, 1 by what, V square divided by 2000 into Cp into T1. Okay, so here I need to put the value of Cp. So value of Cp I'll put now as gamma into R, okay, divided by gamma minus 1. Okay, divided by gamma minus 1. So gamma minus 1, that I will bring it in the numerator. Okay, see, all of you see here, gamma R upon gamma minus 1. So this will go into the numerator. Okay, into T1. Into T1, it is already there. You can see it is that T1 is already there, right? T1 is already there, right? So let us try to further simplify this equation. Okay, so what we can write down here is, okay, see, I'll just try to simplify this as, so is equal to 1 plus V square, 1 plus V square into gamma minus 1 divided by, okay, now this I will write down as, see how I'm rearranging it. Okay, 2 gamma into 1000 into R, 1000 into R into T1, 1000 into R into T1. Okay, because see, all of you see this one. So this equation you can use. Okay, when you can use the equation, when see, this equation you can use when value of R is in kilojoule per kg Kelvin. Okay, so if you are using this equation, okay, when you're using this equation, above equation, okay, let me call this as some equation, let this be equation number 3. Okay, so we will use equation number 3 when in that equation we want the value of R to be in kilojoule per kg Kelvin. Why? Because you can see this V square by 2000, V square by 2000, this term, it is in kilojoule per kg. This V square by 2000, it is in kilojoule per kg. So obviously R has to be in kilojoule per kg Kelvin. Yeah, is that okay? Yes.
Yes, sir.
Okay, now see, but I will write down, but if we have the value of R in joule per kg Kelvin, if you take R in joule per kg Kelvin, then above equation may be written, okay, we can rewrite this equation, okay, as, okay, T2 by T1, okay, is given by T2 dash by T1. Okay, same I'm writing, T2 by T1 is given by T2 dash by T1 is given by 1 plus V square into gamma minus 1 upon 2 gamma, okay, 2 gamma okay, into R into T1, okay, into R into T1. You can see here, right? So this equation you can use when R is in joule per kg Kelvin. So when R is in joule per kg Kelvin, okay, simply the equation will be there, okay. But when R is in kilojoule per kg Kelvin, okay, you need to multiply it by 1000, okay. Yes, is that okay?
Yes, sir.
Okay, so let us rewrite this equation. Okay, now see, in the thermodynamics, okay, in the thermodynamics, okay, there is one term, okay, that is called as local sonic velocity, okay, or this is also known as acoustic velocity. Okay, I will just write down that term. Okay, there is one term, okay, that is called as local sonic velocity, local sonic velocity, okay, or this is also known as acoustic velocity. Okay, it is also known as acoustic velocity, okay, sonic velocity or acoustic velocity, right? Now what is sonic velocity or acoustic velocity? Okay, so it is indicated by A. Sonic velocity or acoustic velocity, it is indicated by A, okay, and A is given by, okay, square root of gamma into R into T, okay, square root of gamma into R into T, okay, where value of R is in joule per kg Kelvin. Value of R is in joule per kg Kelvin, okay. So this is a value of A, okay, what is called as a local velocity, local sonic velocity or acoustic velocity, okay, and A is given by square root of gamma RT, okay. Now you can see here what we are getting gamma RT, right? Gamma RT we are getting here, okay. So let us put this equation, right? Let us put this value, okay. So I will call this as now, okay, let this be equation number 4, okay, let this be equation number 5, okay. So I'll put now, okay, putting, okay, putting equation 5, okay, into equation 5 into 4, okay. I will put that into equation number 4. So let us see what we are getting. We'll get T2 by T1, that is nothing but T2 dash by T1, okay. So is given by 1 plus, okay, V square divided by V square into gamma minus 1, okay, it is kept as it is, okay. V square into gamma minus 1, it is kept as it is. Now the next thing, okay, 2 I'll write down as it is, gamma into R into T, okay, we know that it's a sonic velocity. See, what is sonic velocity? It is square root of R, gamma RT. See, sonic velocity A is the square root of, okay, gamma RT. So when you make it A square, it becomes gamma RT, okay. So this is nothing but A square, this is nothing but A square, okay. So I'll just write down this as one more equation. Let it be equation number 6. Let this be equation number 6. Is that okay? Yes, is that okay? We are getting it as a equation number 6.
Yes, sir.
Okay, now see, this is a very important term, what we used to call it as ramming temperature. So this is very important to calculate, okay. Now what I will do, okay, now see, there is one more term, okay, what is called as a match number, okay. There is one more term, okay, what is called as match number, okay. So match number, I'll just write down, okay. So match number, see, is match number, and which is indicated by M, okay. Match number, it is indicated by M, okay. Now what is match number? Match number, okay, it is the ratio of match number M, it's the ratio of aircraft velocity, it's the ratio of aircraft velocity. Match number, it's the ratio of aircraft velocity, okay, to the local sonic velocity, to the local sonic velocity, okay. This is called as a match number, okay. So it's the aircraft velocity, we know that aircraft velocity is V, okay, divided by sonic velocity is A, okay, just now we have seen. So match number M is the ratio of aircraft velocity V to the sonic velocity A, okay. So we'll put this value, okay. So I'll just write down this as one more equation. Let this be equation number 7, okay. So we'll put this, so putting equation number 7 into equation number 6, we'll put that, okay. So once we put that into the this equation, okay, what we'll get, we will get okay, T2 by T1, or it is same as T2 dash by T1, okay, is given by 1 plus, okay. Now V by A, we know that. What is V by A? V by A is M, right? V by A is M, okay. So I'll just write down these as, okay, 1 plus, okay, 1 plus, okay, gamma minus 1 I will write down as it is, okay, upon 2 I will also write down as it is. You can see gamma minus 1 by 2 I will written as it is, okay, and this term I will write down as M square. See, this V square by A square, see, V by A is M, okay, V by A is M, right? You can see this, yes, all of you, V by A is M, right? So what is V square by A square? It's M square, okay, that is what it is, right? So this is how, okay, this is how we are getting, this is how we are getting the temperature after ramming, okay. So T2, it is nothing but what? Temperature after ramming, okay, that is nothing but, okay. So T2, it's the ideal, T2 dash is the actual, right? Yeah, is that okay with this one? Yes, let me know. Yes, see how was the long derivation we have seen? Is that okay with this one?
Yes, sir.
Okay, so see, one was the inlet condition, two was the exit condition. Now see, once it is getting out of the, see, one is the ambient condition, right? That is the inlet condition. So once it is rammed, okay, it is getting out at point number 2, okay. So point number 2, it's the inlet to the compressor. Point number 2 is the inlet to the compressor, and point number 3 is the exit to the compressor, okay. And in compressor, what happens is, in compressor, work gets consumed, right? In the compressor, what happens? The work gets consumed, okay. So we need to calculate now, okay. So what is the work consumed during 2 to 3? See, during compression, that is during 2 to 3, work gets consumed, okay. So now I'll just write down here, okay. Now here I'll just write down, okay, work consumed, work consumed during compression. Now I need to calculate work consumed during compression, okay. And where occurs during compression? In compressor, okay. This you should understand. Work consumed during the compression in the compressor, okay. How to calculate? Okay, so you know that, how to calculate that, okay. So WC, we used to calculate WC, okay. How to calculate? Okay, that is nothing but how much mass of the air which is present inside a compressor, then Cp of the air, okay, into what? Into change in temperature, okay. So what change, what final temperature we have? Okay, T3. What initial temperature we have? T2, okay. You can see our process is what? Process, you can see here, okay. Process, it is from 2 to 3, okay. So final is T3 minus initial is T2, okay. But you can see, okay, see, when you take 2 and 3, 2 and 3, they are ideal processes, okay. They are 2 and 3, they are ideal processes, okay. But what is about 2 dash and 3 dash? They are actual processes, right? So 2 dash and 3 dash, they are actual processes. So this formula, okay, you can also write down as in terms of actual. See, this is for ideal process. Also you can write down this as mass into Cp into, okay, we want them to be actual, okay. So I'll just, okay, you can see here now, okay. So what I will do, okay, now I will write down only in terms of what? Actual process, right? Okay, because see, every device will have some efficiency, okay. So I'll just write down these as, okay, T3 dash minus T2 dash, okay, T3 dash minus T2 dash, okay. So this is actual. If it is not actual, okay, you can write down it as T3 minus T2, right? You can write down this as T3 minus T2. Is that okay? Yes. From where this formula is came? Yes. From where this formula has been came? Can anybody let me know? From where we have taken formula this? Mass into Cp into change in temperature. Yes.
Work done by compressor, you know.
Yes, this is work done by compressor. So it is mass into Cp into change in temperature. Yes. Is that okay?
Yes, sir.
Okay. So I'll just write down. This is which process? This is process 2 to 3. This is which process? This is process 2 to 3, right? Now let us go to the next process. Okay. See, very simple formula is there, very simple problems are there, right? Try to understand this. Okay, now see, once it is getting out of the compressor, we are supplying it where? To the heat exchanger. You can see we are supplying that in a heat exchanger, that is during 3 to 4. You can see there 3 is the outlet of the compressor. Outlet of the compressor, it is nothing but inlet of the heat exchanger. Okay, so inlet of the heat exchanger, it is 3. Outlet of the heat exchanger, it is 4. You can see this process 3 to 4, 3 to 4. Okay, so 3 to 4. Okay, it is what during 3 to 4 what happens during 3 to 4, air get cools, air get cooled in the heat exchanger. Okay, so air gets cooled in the heat exchanger. Okay, so now we need to calculate. Okay, so this process 3 to 4, okay, it occurs where? It occurs in a heat exchanger, and that is nothing but cooling, right? You can see this 3 to 4 in heat exchanger, heat is lost. Okay, so that we need to again okay, taken into consideration. Okay, so now I'll just write down this as, okay, so what I need to calculate is, okay, I need to calculate the heat rejected in the heat exchanger. I'll just write down now, heat rejected in the heat exchanger. So heat rejected in heat exchanger, heat rejected in the heat exchanger. Okay, during which process? During process, okay, which is that during process 3 to 4. Okay, how to calculate heat rejected? Heat rejected we used to indicate it by QR, heat rejected. So again it is, okay, mass of the air into Cp of the air, okay, into change in temperature. Okay, into change in temperature. Okay, so how you'll calculate temperature? Okay, during 3 to 4, see 3 to 4 is a cooling process. Okay, so obviously temperature at point number 4 is less as compared to temperature at point number 3. Okay, so simply I'll just write down this as, okay, T3 minus T4. Okay, I have not taken here final minus initial. Okay, when you take it final minus initial, it becomes T4 minus T3, and you will get a negative value. Okay, but you already mentioned here heat rejected. So what I taken out of T3 and T4, T3 is greater as compared to T4, because T3 it is before cooling, T4 it is after cooling, right? So obviously T4 will be less as compared to T3. That's why I taken T3 minus T4, provided I already mentioned that it is rejected. Yeah, is that okay? Yes, see here 3 to 4, 3 to 4, it occurs in a heat exchanger, right? 3 to 4, it occurs in a heat exchanger. So instead of 3, you can also write down this as a 3 dash, because 3 is the actual, 3 dash is the, see 3 is the ideal, sorry, 3 is the ideal, and 3 dash is the actual. Okay, so I'll just write down this as T3 dash minus T4. Is that okay? Yes,
Yes, sir.
let me know. Okay, so this much amount of heat is rejected in the heat exchanger. Now see, once it is getting out of the heat exchanger, can you see in the diagram? Okay, if you can see that in the diagram, all of you are you able to see the diagram now? Yes. Now once it is getting out of the heat exchanger, where we are supplying that into the turbine. Okay, we are supplying into the turbine. Okay, so 4 is the outlet of the heat exchanger, that is nothing but inlet to the turbine. Okay, and 5 is the outlet of the turbine. So 4 is the inlet, 5 is the outlet. Okay, and what happens in the turbine? In turbine, work is produced. Okay, so work produced in the turbine, that I need to calculate. Okay, now so that I will write it down now. Okay, so work, you can see here, work, okay, produced, work produced during expansion in a turbine, during expansion, okay, that occurs in a turbine. Okay, that expansion in turbine. Okay, and all of you know that, okay, this is a process which, this is the process 4 to 5. Okay, so let us calculate work produced in the turbine. How to calculate? Okay, same, mass of the air into Cp of the air, okay, into change in temperature we want. Okay, mass of the air, Cp into change in temperature. Okay, so see 4 is the initial temperature, 5 is the final temperature. Okay, so obviously, okay, when it expands, what happens? Temperature drops down. Okay, that means okay, you will get the value of T5 less than T4 because it's an expansion. So T4 will drop to T5. Okay, so what I will take highest temperature. Okay, at the starting, I'll just take it that as a T4. Okay, minus T5, and that is nothing but T5 dash, because T5 dash is the actual. You can see here. You can see, if you can see here. Okay, 4 to 5, 4 to 5, it's ideal. 4 to 5 dash is the actual. Okay, so 4 to 5 dash is the actual. That is what is shown in the diagram. Yeah, is that okay? Have you got how to calculate this work produced during expansion? Yes. Yeah, is there any problem?
No, sir.
Okay, now see, once it is getting out of the turbine, all of you can see, once it is getting out of the turbine, what we are doing is we are supplying that. Okay, where we are supplying that to the cabin. Okay, you can see, purposefully I mentioned, after getting out of the turbine, where does air goes? Air goes to the cabin. Okay, so if you want, what I will do, I'll just erase here only. Okay, so okay, I will just erase this arrow. Okay, so 5 is the outlet of the cabin. 5 is the outlet of the turbine, and that is nothing but inlet to the cabin, right? 5 is the outlet of the turbine. Okay, and that is nothing but inlet to the cabin. You can see this. Okay, I'll just mark the arrow like this. Okay, so this is a point you can see. Okay, so 5, okay, that is the outlet of the turbine. From outlet of the turbine, where the air is going to the cabin. As you can see, this is a cabin. Okay, so from the exit of the turbine, air is going to the cabin, and after that it is getting out at point number 6. Okay, so now see, when the air is supplied to the cabin, obviously it will give the cooling there. Okay, so refrigeration will occur here in the cabin. Okay, so I need to calculate. Okay, so 5 that is exit of the turbine, that is nothing but inlet to the cabin. Okay, and 6 is the outlet of the cabin, or you can call that as a cockpit, cabin or cockpit, anything you have. So we need to calculate now refrigerating effect in the cabin. Okay, we need to calculate now refrigerating effect in the cabin. Refrigerating effect in the cabin. Okay, so we will get refrigeration effect where? We will get it in cabin only. Okay, now how to calculate that? Okay, because when you will get refrigerating effect, okay, when that air will abstract the heat from the cabin. See, whatever the heat that is coming out of the turbine, you can see the heat which is coming, sorry, the air which is coming out of the turbine, we are supplying it to the cabin. Okay, so what that air will do, that air will abstract the heat from the cabin. Okay, so air will abstract the heat from the cabin. So once it abstract the heat from the cabin, what we'll get, we will get a refrigerating effect. Okay, we will get what? We'll get a refrigerating effect. Okay, so if you want, okay, I will also write down this as, okay, refrigerating effect, or also we can call this as heat absorb in the cabin. Okay, one additional term I'll just write down here, refrigerating effect. Okay, or heat absorbed, or we can also call this as or heat absorbed in cabin. Okay, how to calculate heat absorb in cabin? Okay, I'll just write down this as, okay, refrigeration effect. Okay, RE, okay, is given by, or if you want more specific, okay, I'll just write down simply in terms of QA, that is heat absorb. Okay, that we what we used to do na, QA, heat absorb. Again, same formula, mass of the air, okay, into specific heat of the air, into change in temperature. Now you can see, okay, so 5 is the inlet to the cabin and 6 is the outlet to the cabin. Okay, so what I will do, okay, 5 is the inlet to the cabin, 6 is the outlet to the cabin. Now see what happens. Okay, when the air which is coming out of the turbine, when you supply it to the cabin, what happens, that air abstract the heat from the cabin. Okay, so air abstract the heat from the cabin. As a result, what happens, temperature of the air gets increased. Okay, So what happens with the air? The temperature of the air gets increased from T5 to T6. Is that okay? Let me know. See, whatever the air that is coming out of the turbine, whatever the air that is coming out of the turbine, we are supplying it to the cabin. Okay, so what that air will do? It will abstract the heat. So when that air will abstract the heat, what will happen? Okay, temperature of the air gets increased from T5 to T6. Okay, so temperature of the air gets increased from T5 to T6. Okay, so when that air will abstract the heat from the cabin, what will happen? Cabin gets cooled, but air gets hotter. Okay, but air gets hotter. Okay, is that okay? Yes. So see,
Yes, sir.
okay, so I'll just write down this as, okay, so this is the final temperature. I'll just write down this as a T6. Okay, final temperature is T6 minus initial temperature is T5 dash. Initial temperature is T5 dash, right? So this process, it is occurs during 5 to 6. Okay, so what happens with the temperature of the air? It will increase from T5 to T6. Okay, so final temperature T6, it is greater than the initial temperature T5. That's why I written T6 minus T5 dash. Is that okay? Yes.
Yes, sir.
See, if you want, I will repeat. See, this air, which is supplied to the cabin, it abstracts the heat from the cabin. Okay, so when air abstracts the heat from the cabin, air gets heated. Okay, that means temperature of the air gets increased from T5 to T6. But what happens with the temperature of the cabin? The cabin gets cooled. Okay, when you remove the heat from the cabin, it gets cooled. But what happens with the temperature of the air? It got increases from 5 to 6. Yeah, is that okay? Yes. Yes. Is that okay?
Yes, sir.
Okay, now see, all of you know that we used to measure the refrigeration. Okay, how we used to measure the refrigeration? We used to measure the refrigeration in terms of tons of refrigeration. See, whenever we require any AC, okay, when we need to buy the AC, okay, we used to calculate the requirement of the AC in terms of ton. Okay, so see, if you want to define me what is ton, okay, so 1 ton, it is nothing but, okay, what amount of refrigerating effect, okay, the ice is producing. Simple example. Okay, let us take one ton of ice. 1 ton of ice. Okay, that means 1,000 kg of ice. If you take, okay, and if that 1,000 kg of ice will start to melt, okay, when 1,000 kg of ice will start to melt at 0 degrees Celsius, okay, whatever the refrigerating effect or whatever the cooling effect that is produced, it is called as 1 ton refrigeration. It is called as 1 ton of refrigeration, right? So what is 1 ton of refrigeration? If you want, okay, I will also write down here. Okay, okay, so 1 ton, okay, 1 tons of refrigeration, okay, 1 tons of refrigeration is nothing but, okay, is is amount of is the amount of refrigeration effect, amount of refrigeration effect, refrigeration effect, okay, produced produced by produced by uniformly melting, by uniformly melting uniformly melting, okay, 1 ton, by uniformly melting 1 ton, okay, that is nothing but 1,000 kg of ice, 1,000 kg of ice from and from at 0 degrees Celsius, from and at 0 degrees Celsius in 24 hours. In 24 hours. Okay, so what is simple? Let us say you have 1,000 kg of ice, okay, and you are maintaining it at 0 degrees Celsius. Okay, so how much refrigerating effect it is producing? Okay, so that is nothing but 1 ton of refrigeration. Okay,
सर
so
वो मेल्ट कहाँ से 2 डिग्री पे?
Can repeat?
तो 0 डिग्री पे अगर मेंटेन करेंगे तो मेल्ट कहाँ से होगा?
Yes, see that is the question. Na? See, 0 degrees Celsius. See, it is a freezing point as well as it's a melting point as well. Na? So at 0 degrees Celsius, you will get both. You will get both. You will get a liquid as well as you will get a solid. See, if you want, I will give you example. At 0 degrees Celsius, what you have ice. Similarly, at 0 degrees Celsius, okay, you can have also water, right? Yes. Yes.
हाँ सर.
Okay. So amount of heat required so as to convert ice at 0 degrees Celsius to the water at 0 degrees Celsius, it is called as latent heat of ice. Okay, have you remember this term? What is called as latent heat of ice? Yes, in the thermodynamics, we have made some diagram like this. If you are able to collect, okay, some diagram like this we have made. Okay, TH diagram. Are you able to
Yes sir.
remember such diagram? TH diagram. Yes. So amount of heat requires to convert ice at 0 degrees Celsius to the water at 0 degrees Celsius, that is called as the latent heat of ice. Okay, so this is somewhat related with the latent heat. Okay, that is refrigeration. Yes, is that okay? Yeah, one who has asked the doubt, is that okay with the doubt? Yes, let me know. Yes, you can respond. Yes.
सर लेकिन एक टाइम पे बर्फ तो पूरी पिघल जाएगी ना?
Yes. How much time it is given? Within 24 hours. Within 24 hours, you need to melt 1000 kg of ice at 0 degrees Celsius. We have sufficient time. 24 hours to melt 1000 kg of ice at 0 degrees Celsius. So whatever the refrigerating effect that is produced, it will be a 1 ton. Right? Yes. Is that okay?
Yes sir.
Okay. Now see, so when you talk about 1 ton of ice, okay, 1 ton of ice, it requires, okay, 1 ton of ice requires, okay, 335 kilojoule per kg to melt. Okay, so this much amount of heat is required to melt. Okay, see all of you, 1 ton of ice, okay, how much heat it requires? It requires 335 kilojoule per kg to melt. See, this much amount of heat it is required it to melt. That means simple. See, this much amount of heat is required to be supplied to melt it. That means what? This much amount of refrigerating effect it will produce. Is that okay? Are you able to get
Yes
it?
sir.
See, this much amount of heat it requires to melt 1 ton of ice. Okay, so that means what? This much refrigeration effect will be produced. Yes. So that means if you want me to calculate 1 TR, okay, now 1 ton I will write down as 1 TR. Okay, see if you want.
सर टॉर क्या होता है फिर? TOR.
क्या
TOR में भी कैलकुलेट करते हैं ना सर?
TR, not TOR. It is TR. See, TR it is nothing but ton only. Okay, 1 ton it's nothing but 1 TR. Okay, same I'm writing now. Okay, yes. So 1 TR, it is nothing but how much we need to melt, how much? 1000. We need to melt 1000 kg of ice. And for per kg, how much we require? We require 335 kilojoule per kg. Is that okay? Okay, see, all of you. See, for melting 1 kg, we require 335 kilojoule per kg. See, for melting 1 kg, we require 335. So for melting 1000 kg, how much we require? 335, 1000 into 335. Is that okay? Kilojoule, right? In 24 hours. Okay, this is required to in 24 hours. देखो simple बोल रहा हूँ, देखो. See, for melting 1 kg, we require 335 kilojoule. For you see here it is written. For melting 1 kg, we require 335. So for melting 1000 kg, we require 1000 into 335 kilojoule. Okay, in how much hour? In 24 hours. Okay, so it is given by, okay, so 1000 into 335. Okay, now this is an hour. Okay, this is an hour. Okay, so now this hour I will convert into minutes. Okay, so 24. See, all of see here, 1000 into 335. Okay, this much heat it requires in 24 hours. Okay, so in minutes. Okay, how to convert hours to minute? Just multiply it by 60.
60.
Okay, so multiply by 60, simple. That means what? You need to divide that quantity by 60, right? So this term, if you calculate, okay, it is coming to be 232.6, okay, kilojoule per minute. Kilojoule per minute, because see, I have divided by 60. Okay, so if you want, here only I'll just write on that. Okay, here only I'll just write on that. Why I divided by 60 is I want this answer to be in kilojoule per minute.
Understood.
Yes. Okay, so is given by how much answer I'm getting? I'm getting 232.6 kilojoule per minute. Okay, so 232.6 kilojoule per minute. Okay, so what do you understand by 1 ton? 1 ton or 1 TR. Okay, it is nothing but how much? 1 ton or 1 TR. It is nothing but, okay,
Time taken to melt 1 ton of ice in 24 hours at 0 degrees
yes,
Celsius.
exactly. And how much it is? 232.6, okay, kilojoule per minute. Okay, but see, in practice we used to take it as 210. Okay, this value we used to take it as 210 kilojoule per minute. Okay, so in further calculation, okay, we will use this value. Okay, which value we will use is, okay, this is the value which we'll use. Okay, that is 210, okay, kilojoule per minute. Yeah, is that okay?
Yes, sir.
1 ton we will take it as
Yes, sir.
210 kilojoule per minute. Yes, is that okay? Yes.
Yes, sir.
Okay, so just we'll take okay, within 2 minutes we will finish this. Okay, now see, next thing it is about, okay, the mass flow rate. Okay, now see, mass flow rate. So if q tons of refrigeration, okay, if q tons of refrigeration, if q tons of refrigeration, okay, is the cooling load in the cabin. Okay, if q tons of the refrigeration, okay, I want q ton in the refrigeration cabin. Okay, so if q tons of the refrigeration, I'll write down refrigeration is required in the cabin, is required in the cabin. I want, see, what is the capacity of the cabin? It's q ton. Okay, so I want q tonnage of refrigeration in the cabin. Okay, so mass flow rate. Okay, what is the mass flow rate? Then air required, I'll just write down, then air required, then air required for refrigeration, then air required for the refrigeration. Okay, so air required for the refrigeration, that is I need to calculate mass flow rate. Mass flow rate is given by, okay, mass flow rate is given by ma. Okay, what is the mass flow rate? Mass flow rate, it is indicated by ma. Okay, so mass flow rate, it is given by, mass flow rate of the air is given by, okay, 210 q. Okay, see here, I required q tonnage of refrigeration. Okay, I required q tonnage of refrigeration, but what is 1 ton? It is 210 kilojoule per minute. Okay, so that is the reason why I multiplied by 210. See, I require q, see, 1 ton is 210, then q ton is what? Q into 210. Yes, is that okay? Yes.
Yes.
Divide by what? Cp into, okay, T6 minus T5 dash. T5 dash. See, all of you, mass flow rate I need to mention. Okay, so it is given by what? Okay, this had, see, this Cp into T6 minus T5, it is nothing but what? You can see Cp into T6 minus T5, that is the refrigerating effect, right? That is nothing but refrigerating effect. All of you see here, what value of q, see from this equation. Okay, mass flow rate ma, how will write on ma is given by qa divided by Cp into T6 minus T5 dash. Is that okay? See here, ma is given by qa divided by Cp into T6 minus T5 dash. Yes, is that okay? All of you, is that okay or not? Okay.
Sir.
I'll just write down here one more time. Okay, it is given by QA divided by CP into, okay, what I written? CP into T6 minus T5 dash. T6 minus T5 dash, right? So QA, heat absorb. How much heat is to be abstract from the cabin? It is Q ton is to be abstracted. And Q ton, it is nothing but what? 210 into Q kilojoule per minute, right? Divide by CP into T6 minus T5 dash. Is that okay? Yes.
Yes, sir.
Okay. So this
Yes,
is how
sir.
we calculate. This is how we calculate mass flow rate. Okay. Now see, only two terms are remaining. I will just fastly go through it. Okay. Power required. Okay. I need to calculate now power required for the refrigeration system. How much power is required for the refrigeration, okay, system? Power required for the refrigeration system. Okay. How much power is required? So power obviously required. It is in the form of what? Compressor. Okay. So for compressor, how much work is consumed? MA into CP into T3 dash minus T2 dash. Okay. You can see that. Okay. So power is given by, okay, work done by compressor divided by 60. Simple. Okay. So it is mass of the air into CP into T3 dash minus T2 dash, okay, divided by 60. Because see, the above quantity will be in kilojoule. Okay. This will be only in kilojoule per minute. Okay. So we need to divide by 60. Right. So this will be in kilojoule per second. Okay. Is that okay? And that is nothing but kilowatt. Right. This is nothing but kilowatt. Is that okay? Yes. Let me know. Yes. All of you.
Yes, sir.
And last term, that is COP of refrigerating system. This is only important. COP of the refrigerating system. Okay. How to calculate COP of the refrigerating system? It is given by, okay, desired effect.
Work done by compressor.
Upon work input, right? Yes, upon work input. Right? Desired effect, that is cooling. Okay, cooling. In cooling, what happens? Heat is abstracted. How much heat is abstracted? MA into CP into T6 minus T5 dash. I'll just write down that. So MA into CP into T6 minus T5 dash. Okay, because this we will get it in cabin. This desired effect we will get it in cabin. Okay, that is heat abstracted I've written, right? T6 minus T5 dash, right? And work input, just now I written in the compressor, MA into CP into T3 dash minus T2 dash, right? Yes. Is that okay?
Yes, sir.
Okay, so what value we got? Last equation I'll write down. Okay, T6 minus T5 dash upon T3 dash minus T2 dash, right? Minus T2 dash. Okay, so this is how we will calculate the COP of the refrigerating system, right? Is that okay? Yes.
Yes, sir.
Okay, so this is the
Yes.
important term. Why we are done this analysis? Because we need to calculate COP. So it is T6 minus T5 dash upon T3 dash minus T2. Is that okay with this one?
Yes, sir.
All of you, is that okay? Okay. So with this, we will conclude the today's session, and in the next session, we will see a simple air evaporative cycle. Okay. We will see what? Simple air evaporative cycle. Okay. This part which I'm showing, simple air evaporative cycle, we will see in the next session.
Okay, sir.